Good data structures often make the difference between an efficient algorithm and an inefficient one. So in the next few videos, we'll see a variety of elementary data structures. You've probably seen many of them already in your CS1 or CS2 classes, but we're going to look at them under a new lens from the standpoint of efficiency. So we're going to see how each of these structures are defined and implemented, and most importantly, how efficient each operation that can be performed on a given data structure is. So let's start with stacks. This is a container that stores any arbitrary object so that items are inserted and deleted according to the last in, first out scheme, much like a stack of papers. So an item in it is added with the push operation, which adds an element to the top of the stack, and an item is removed with the pop operation, which removes whatever element is on top of the stack. So there's also the operation top, which will just return the last element on top of the stack without actually removing it. And then this and every other data structure that we're going to talk about also has functions size and is empty in order to determine the number of elements in it. So there's a lot of applications of stacks. Directly, this can be used to keep track of web history. As a new page is visited, its URL is pushed onto the stack, and if you press the back button, the URL is popped off the stack. The same idea is also used in a text editor to keep track of edits. So character changes, insert or removing a character, are pushed onto the stack so that, again, if you press the undo button, then it reverses the edit. This is also how the C++ runtime environment keeps track of method calls by pushing it onto the stack. There's also a lot of indirect applications of stacks. So this can be used as an auxiliary data structure for an algorithm, meaning that this isn't, maybe an algorithm doesn't necessarily take as an input a stack or outputs a stack, but instead it internally uses a stack in order to accomplish some task. So it can also be used as a component to build other more complex data structures, so a larger data structure that internally has a stack. So let's see how a stack can be implemented. So there's a few different ways where we could implement a stack, but we're going to look at how to do so with an array. So we have a variable t, which is an integer, and this is used to keep track of the index of the top element. So anytime we push an item onto the stack, we push it immediately after this top of the stack, and then we increment this counter. So the push operation here takes an object, checks first to make sure that we actually still have room left in the array where we could place this new item. If we don't, if we run out of space, then we throw an exception. So this check is constant time, and throwing an exception is constant time, one primitive operation. Otherwise, assuming we still have space left over that we could place an item at the end of our array-based stack, then we increment this counter, we place the new object at this counter, and this is our new top of the stack. So push is pretty simple. This is a constant time operation. It's big O of 1, constant time. So in the worst case, this has a constant number of primitive operations. Pop can be executed similarly. So we have, again, we check to make sure that there's items left to be popped off the stacks, and if there aren't any, then we throw an exception. Otherwise, if we do have something to pop, then we decrement our, let's say we're popping this item here, we decrement our top of stack index, and then we return that old item which was at the top of our stack. So again, this is a constant time operation because everything that we have inside of this algorithm, we have only a constant number of primitive operations. We can also implement top similarly to this, where we just return whatever element is at this index t without actually removing it. So top is constant time as well. And size and is empty we can implement in constant time just by returning the number of elements that we have is whatever our index top of stack t is plus 1, and then is empty, that function we can just check, return whether this is equal to 0 or not. With any data structure that we're going to talk about, we can always implement size and is empty in constant time by just maintaining a counter of how many items we've added and removed. So all of the operations that we have here run in constant time. But the downside is that in this implementation, so we are using an array, but an array is at a fixed size, and an actual application may need more or less memory. So in order to implement a stack which more realistically can shrink and grow with the size of the input, we're going to use an extendable array. So the idea with this is that we go to push an item, and rather than throwing an exception like we did before, if we find that our array is full, so maybe this is our array here, we have 3 items and we have no other room left, then rather than throwing an exception, we'll create a new array, something a little bit larger, right, of some size, and then we'll copy everything from our old array into our new array. So we have to loop through every item that we have here and place it into our new array. Now we've got all of this extra space where we can place new items, including the one that we wanted to push initially. So rather than throwing an exception, we create a new array which is even larger, then copy every item from our old array into our new array. But the only question becomes, how much larger really should we make our new array? There's a couple strategies that we could use. And in fact, you probably implemented something like this when you worked on the string project in CS2. So if we use the incremental strategy, then every time we fill our array, we just increase the size of our new array by some constant. So this means maybe we have an array of size 3, and then when we finally fill this up, we create a new array of whatever the size our old one is plus 3. Okay. And then once we fill this one up, we take whatever the size of our old array was again and increase it by the same constant. So in this case, this would be 3. So always increasing by some constant, see, 1, 3, 5, something which doesn't depend on n at all. With the doubling strategy, every time we create a new array, we double the size. So if we started, let's say we started at 3 again, once this is filled, then we create another array of size whatever the old size was, times 2. So now we've got 6. So now once this is completely filled, we create a new array. Let's say this has 6 items in it, and we had another 6 at the end of it. Okay? So every time we create a new array which is twice the size of the old array. So this is just 2 different strategies we could use. Which one should we use? Well, let's see how they compare. Which one is more efficient? Let's see. In our push algorithm, what do we actually accomplish? Well, it kind of depends on whether our array is full or not. So if we do have space left over, if this condition is false, then we skip all of these lines of code and all we do is we execute these last 2, which is adding an element to the last, to our top of stack, to our new top of stack. So just these lines here alone are constant time. So if that's all we ever do, then our push operation is constant time. But in the worst case, which we want to consider the worst case, then our array is completely filled and we have to create a new array, and in doing so we copy everything from our old array into our new array. We've got n items in our old array. When we put all of those n items in our new array and we copy each of them over, each copy is one primitive operation. We have to access this index and then we have to assign it the old value that we had here. So each copy is constant time and we have n copies. So if we have to go through these lines of code, our total running time is linear. So sometimes push is linear time, other times it's constant time. So the worst case running time of push using either one of these strategies is linear time. Okay? But let's think about this a little bit differently, because it's not always linear time. It's just some of the time. So if we were using the incremental strategy and we filled up this array and we created a new one, and let's say we always added 10 more spots to the end, right? Then it would take us 10 times until we reached the end of this part where we had to create a new array. So when we have an algorithm like this where sometimes it has a sort of variable performance like this, where sometimes push is constant, other times push is linear, this is a good opportunity where we can use what's called amortization. So this will give us a better picture of how we can compare these 2 strategies. So this is a useful analysis tool for understanding the running time of algorithms that have steps with wildly varying performance. So for example, our push operation we saw sometimes ran in constant time, other times it ran in linear time. So we use amortization when we're interested in the total complexity over a sequence of calls to that operation. So our average cost per our amortized cost is the average cost per operation over the entire sequence. So this is unlike an average case analysis because there's no probability or expectation involved. Instead, we're going to focus on each operation separately. So this considers the interactions between all operations by studying the running time of a series of those operations. So we'll look at what it would cost to call the push operation n times. So T of n is the cost of calling push a total of n times. So the total running time after calling push n times. And our amortized cost would then be the average of what it costs to call push all of those n times divided by the n times that we called push. So let's look at the amortized cost of push using the incremental strategy. So suppose we start with an empty stack represented by an empty array. So in order to determine the total running time over a series of n calls to push, we want to tally up all the primitive operations so that we can put this in big O notation. So we already know which operations are going to result in higher order terms. Those operations which occur the most frequently when we insert an item and when we have to copy an item over to our new array. So our total running time is proportional to however many times we insert, which if we're calling push n times, then the total number of times that we insert an item is n. And then we just have to figure out how many times we copy an item. So let's suppose for the moment that we replace the array k times. We'll see why this is equal to n over c in a moment. But let's just say we have to replace the array k times. And remember, we started off with an initially empty array. So first we have nothing initially, and then the first time we have to replace this array, it's because of our first push. So we create a new array, which is of size 1, and we place this item here. And then the next time we have to, or we'll create an array of size c, let's say, however many elements c is. So we'll be able to place C items in here, push C items in here until we have to create a new array once this is full. So once we go to add the C plus 1th item, we'll have to create a new array, which is of size our old array C, however many that was, and then we'll add an extra C items at the end of it. So we already accounted for what it costs to insert items. We know we're going to insert n items total. So how much we have to copy over, at least in this case, would be we've got these C items we have to put in our from our old array into our new array. And then once we finally fill this up, we have to create another array of size 3C. Okay. And how many items we have to copy over? We've got 2C, many of them, everything from our old array. So at first our old array was of size C, then it was of size 2C, and then 3C, because every time we added just an extra C elements onto it. And since we replaced our array k times, then the last time we did this, we had k times c items to copy over. Okay. And let's suppose in the worst case, this array that we had created of k times c items was completely filled, meaning we had k times c is equal to n. That array of size k times c was full, which means if we just solve for k here, that k is equal to n over c. Okay, so this is the total number of operations we incur, the number of inserts plus the number of copies that we had to make, copying from our old array to our new array. Now we can factor c out of this right side sequence. So we have c times here 1 plus 2 plus 3 plus 4 all the way up until k. We've just factored c out of this. And it will help to remember again that sequence, that if we're taking the sum of 1 plus 2 plus 3 plus all the way up until the first k items that we're adding together, this sequence in parentheses is equal to k times k plus 1 all over 2. So if you don't remember that one, that might be a good one to write down somewhere so you can refer to it again later. So now we have our total cost of calling push n times is equal to n plus this sum here. So that means that since c is a constant, we're going to get rid of that. Once we want to put this in big O notation, we get rid of any constant coefficients. So our half we'll get rid of as well. And we're left with n plus k squared, right? Once we get rid of any coefficients here and lower order terms. But we also know what k is. K is equal to n over c. So once we substitute in here n over c, all of that squared, we're left with this big O notation. This is also big O of n squared, because c is just some constant. We're going to drop that when we put this in big O notation. Right? So our total running time of calling push n times, the total cost of all those n calls to push, if we're using the incremental strategy, is big O of n squared, which means our amortized cost for a single push operation, this is the average over a series of calls, this is how we calculated this. This was the total cost of all n calls to push divided by, we had called push n times, and we know that this was big O of n squared. Dividing that by n, we're left with big O of n. So the amortized cost of a single push operation, if we're using the incremental strategy, is big O of n. Yeah, that's no better than what we had for the worst case running time of push without using amortization. So we'll see really why amortization is useful when we get to the doubling strategy. So let's see that next. So we're going to look at the total time, again, for a series of calls to our push operation, but using the doubling strategy. So remember, again, with the doubling strategy, in this case, we start off with an initially empty array, and then we'll create, let's say we have an element of size 1 when we want to push our first item. So then our array is of size 1, we fill that. Once we fill that, we double the size of our array. Now we've got 2. Once that is filled, we double it again. So here we've got 4, and then once that gets filled, again, we double it again, we get to 8, 6, 7, 8, and then once that gets filled, so every time we keep doubling it, we repeatedly double it. So we know we're going to call push n times, so we've got n inserts that we make, and then we want to figure out this last sum. This is how many copies we've made. And we can assume again that we've replaced the array k times. We'll see why this is equal to log n in a moment. But let's just say for the moment we replace the array k times. So why do we have this many copies? Well, this is based on how big the array is, the previous array, our old array that we have to copy over. So initially we have an array of size 1, and then we doubled it, so we had an array of size 2, and then since we doubled it, this was an array of size 4. So note that this is 2 to the 0th power, 2 to the first power, 2 to the second power, and every time we do this, we take it to the next power, right? So if we end up replacing this k times, then when we're done with this, we have an array of size 2 to the kth power. Okay? And again, just like we did in the last instance, to see kind of the worst case here, let's say this array of size 2 to the kth power is completely filled with elements. So we have this many spaces in our array, 2 to the kth power, but this is equal to n. Each one of those spaces is filled. So the question becomes, we want to solve for k at this point. What value of k will make 2 to the kth power equal to n? So we want to think back to the properties of logarithms. Right? So if we take the logarithm of both sides of this, we have log n is equal to log of 2 to the kth power, using log base 2 here. And log of 2 to the kth power, this is just equal to k. So k is equal to log base 2 of n. This kind of idea, before I continue yet, this kind of idea is actually really important. It comes up quite frequently when we evaluate the runtime of an algorithm, so keep this in mind. And again, write this part down if this didn't make sense for you. So the number of times that we had to, beginning at the value 1, repeatedly double that value, double that value, double that value, until ultimately we reached the number n, the total number of times that we had to keep doubling was exactly log n. Okay? So one could equivalently think about this as, if we start with the value n, how many times do we have to keep dividing by 2, dividing by 2, dividing by 2 until we reach 1? And that's also log n. So again, this is going to come up quite a lot when we evaluate the runtime of an algorithm. How many times do we have to double starting with 1 until we get to n, and that value is log n. This is how we're going to get log n in some of our big O notation. Okay, but I digress just a little bit here. So back to our doubling strategy. So we know that the number of copies that we make is 1 plus 2 plus our next array was of size 4, our next array was size 8, and each time we're copying over those elements into our new array, which is double the size. So this is the total number of inserts plus the total number of copies we made. Okay, now for the next, how we get to the next part here, it will help to remember this geometric series. So we're taking the sum of all of the first k powers of 2 and just plugging in this equality here. So this entire summation is equal to 2 to the power of k plus 1 minus 1. Okay, now we already solved for k. We know that k is equal to log base 2 of n, what we had up here. So we're just substituting that in how we get to the next line, right? So k is equal to log base 2 of n. Now we know that 2 to the power of, 2 to the power of log n plus 1. We can separate this out. This is just from the rules of exponents here. So we have the same base for log n and the same base for 1, which is 2. So we have 2 to the power of log n times 2 to the power of 1. So just this part here, these two things are equivalent. All right, so now we've got 2 to the power of 1. This is equal to 2. And then 2 to the power of log n. Remember that log n, and again, we're working with log base 2 of n. Log base 2 of n is what power we have to take the base 2 to in order to make it equal n. So if we take 2 exactly to that power, we're left with n. So 2 to the power of log n is equal to n, and 2 to the first power is equal to 2. So now that we're at this point, we just add these together. We're left with 3n here minus 1. So t of n, our total cost of calling the push operation n times, is big O of n. We get rid of these lower order terms and this constant coefficient. So our total running time after calling push n times using the doubling strategy is big O of n, which means that our amortized time, which is the average over calling this n times, is our amortized time is our total cost over n. And we know that t of n is big O of n. When we divide that by n, we're left with 1. So the amortized cost of push, if we use the doubling strategy, is constant. So let's kind of remember now how this compares to the push operation, the incremental strategy, what we had. So keep in mind, we had the incremental strategy and the cost, the amortized cost of push. When we used the incremental strategy, we had something worse. We had big O of n. So when we were using the incremental strategy for an array-based stack, the amortized cost of push was linear, but now we see that if we use the doubling strategy instead, our amortized cost of push is constant. Okay, now the approach that we took to finding this value, this amortized cost, for both the incremental strategy and the doubling strategy, we used an amortization method of essentially just directly counting these primitive operations up. We're going to see another approach to find the amortized cost. So we already know what the amortized cost is just because we just solved for it, but I want to show you a different way that you could find, determine this amortized cost. Okay, so the accounting method is just another way of finding the amortized cost of an operation. So it views the computer as a device that needs $1 for each primitive operation. So our task is to set up an amortization scheme for charging operations. So for example, if we want to find the amortized cost of push, we would have to determine some amount, let's just say $5, that we have to pay the computer every time we call push. And the key is that the computer must always have enough money in its bank from what we paid it in order to pay the cost of each primitive operation. So we pay the computer for the operation we want to figure out the amortized cost of, for push, for example, and the computer keeps that money and uses it in order to pay for the primitive operations. So the amortized, so if we can satisfy that the computer always has enough money in its bank in order to pay the cost of each primitive operation, then the total cost of these series of operations is no more than the total amount of what we gave the computer. So you can think of this as the computer has to pay not in time, but in money. So our amortized cost then is no more than the total amount that we charged, that we ended up paying the computer, divided by however many times we paid it. So this is the total amount paid for all operations divided by the number of operations. So the benefit of this kind of approach, of this accounting method to determine amortized running time, is that we can overcharge some operations that execute only a few primitive operations in order to help out on other operations later on that have to execute many primitive operations. So let's see this applied to the doubling strategy now. So let's use this accounting method to find what the amortized cost of push on an extendable array based stack using the doubling strategy. So how much did we charge for a push operation? If we can guess the correct amount, then this gives us already the amortized cost. We just have to show that it's enough. So why pay for more than what we have to? Let's just say we charge $1, and let's see if this is going to be enough. So I'm going to keep track here of how much balance we have so far, how much the computer balance is, plus how much we paid the computer, how much the computer has to use, how many primitive operations it has to incur. And again, we're thinking of, in this example, inserts and copies. And then how much leftover balance we have. And this will kind of bring into the previous balance. So let's consider the first time we call push. So we have an array of size 1. Initially, we have no money. We're going to pay, in this case, we're charging $1, so we're going to give the computer $1. And how much does the computer have to use? In this case, it has the array of size 1. It just has to actually insert that element in, which costs 1 primitive operation. We have no money remaining. We paid the computer $1, computer uses $1, we have nothing left over. So the next time we do this, we still have a $0 balance. And this was our first push. In our second push, we've run out of room here, so we have to create a new array of size 2, because we're doubling this. And we pay the computer $1 for the second push. We have nothing left over, so the computer has a total of $1 to work with, but how much does it actually need? So it has to copy this item over, which is $1, and it needs another $1 to actually place that second item. So it needs $2, which means we have a negative balance already. So $1 isn't enough here. We need a good guess. That doesn't give us enough money, though, to copy old elements. So let's try $2. So we're going to do the same approach we had before. We've got no money to work with. Now we're going to pay the computer $2 each time. And how much money does the computer actually need? So the first time we do this, we have an array of size 1. The computer needs $1 in order to actually push that element on, to insert it into that index of the array, which means now, since we paid $2, we have $1 left over. So now let's look at when we're going to carry that $1 for the next time. So when we push our second item, we have to the computer has to create a new array, twice the size. Now we give the computer $2 when we pushed this second item. So now the computer has a total of $3 to work with. And how much does it need? It needs $1 to copy over this old item into the first spot, and another second $1 in order to push our second item. So the computer needs $2, it's got $3, which means we still have a leftover balance, which is good. So now let's look at the third time we call push. So we still have $1 left over from the previous iteration. We're going to pay the computer again $2 for pushing this third item. But how much does it need? It's run out of room from this old array, so it has to create a new array of size 4, because we are doubling. And it will need $1 to copy over this old item, another $1 to copy over this old item, and then a third dollar in order to push that third item. So the computer uses $3, and now we have a balance of 0. Uh-oh. Okay, now let's look at when we push the fourth item. We're nearly done here. So we have a leftover balance of 0. We pay the computer $2, but in this case, we still have room in the old array that we can use. So the computer doesn't have to create a new array, it can just place that fourth item here. So it only uses $1 to push that fourth item because it's using our old array, which means we still have a leftover balance of 1. Okay, so now this is where we're going to run into problems. Let's work with pushing the fifth element. We have $1 left over, we pay the computer $2, so it's got $3 to work with, except now we've filled up this array of size 4, we have to create a new array of size 8. Whoops. So we've got 4 items here, and then another 4 items here. Okay, now we have to copy over the first 4 items from our old array, so that's already $4. And then we need another $1 in order to place this fifth item at index 5 of our array. So the computer has to use $5. Oops, and it only had a total of $3 to work with, which means we're short at least $2. So this isn't enough money, unfortunately. Okay, so $1 isn't enough, $2 isn't enough. We need to find a charging scheme that is sufficient here. So we need to have a good guess. Alright, so we can repeat the same process as what we did before, but you'll see that when we charge $3, we don't run into any of the same problems where we had before. But in order to show that $3 is actually sufficient enough for push, that the computer never runs out of money, we need some kind of an argument to show that that's always the case. Otherwise, it's possible that maybe after the 500th push we'll have a problem. We don't know yet. So we need to prove the computer would always have enough money if we charge $3 for a push. So the main idea here is that when we charge $3, we use one of those $3 in order to pay for the push, and then we get to save up with that element an extra $2, which will help to cover the cost of copying all of the other items over. So let's say we have a $0 balance at the moment, and we've already placed the first 2 items in our array, and we have no money to work with just yet, but when we push this item here, we pay the computer $3. It uses $1 in order to actually place the item at index 2, and then it saves $2 extra here. Okay. And then when we push the next item, again, we pay $3, the computer uses $1 in order to actually place it here, and then it can save $2 extra. Now, this money here will pay for, now that we've filled this array, all the money that we've kept, the second half of our array each element has $2, so these $4 will pay for copying all 4 of these items, just the first 4 items, into our new array. So now that we're at, let me do this one more time now because this is kind of arbitrary. Let's say we had any sized array, right? I know it says 7 here, but let's just say this was of any size, where we've got, let's say, k items in the first half and k items in the second half. So we had already had enough money to pay for this first half, right? Now, every time we push an item into the second half, so we pay $3 to push this item, we are able to save $2. So with every item that we push, we save $2. So we've got a total of 2k items, but in the second half of our array, those last k items, we saved $2. So we have a total of $2k to work with. So when we have to copy over all of those 2k items, once this is completely filled, we've got $2k in order to cover it. Okay? So the computer will never run out of money this way. So because we charged $3 here, the total cost that we ended up paying, t of n, okay? We ended up calling this function n times, We know that the total cost, since the computer was able to cover all primitive operations, all costs of primitive operations, and we gave the computer $3 each time, we know that our total cost T of n for calling push n times is no more than 3n, 3 times n, which means that our amortized cost is, the amortized cost here, this is equal to T of n over n, which is just 3. You'll notice this is exactly the same amount that we charged. So this is our amortized cost for one call to push, and this is constant. So our amortized cost for push using the doubling strategy is constant. Now this is a little bit different way of calculating the amortized cost using the accounting method. It requires a little bit more careful guesswork, but then we just have to be careful to show, as we did here, that however much we charge really gives the computer enough money in order to cover all primitive operations. Okay, that wraps up this video. You'll see some other elementary data structures in the next.